In 2017, a team of scientists drilled core samples from ancient Roman harbour walls that had been sitting submerged in the Mediterranean for nearly 2,000 years. They expected what you'd expect: degradation, cracking, the slow dissolution that happens to any material left in salt water long enough. What they found was the opposite. The concrete wasn't weaker. It had rare crystalline minerals growing inside it that didn't exist when it was first poured. Interlocking crystal plates called tobermorite threading through the structure like a slowly grown internal skeleton. The seawater hadn't attacked the concrete, it had fed it. The longer the Roman walls sat underwater, the denser and more reinforced they became, at a level you can only see through an electron microscope. The team published in the journal American Mineralogist. The engineering world took notice, and then, quietly, the implications began to sink in. Modern concrete, the material holding up every coastal seawall, every bridge pier, every offshore foundation you've ever walked past, starts degrading the moment seawater enters it. Salt ions cause calcium leaching, sulfate attack, expansive mineral growth that fractures the matrix from the inside out. A well-designed modern marine structure gets maybe 50 years before major remediation is required. Some fail in 30. Coastal cities are currently spending billions every decade just to maintain structures that are aging faster than they can be repaired. Roman harbour walls built under Emperor Augustus have been sitting in the same seawater for over 2,000 years, and they're still getting stronger. That's not accident, that's not over-engineering. That's a formula. Here's the thing, we've known Roman concrete was durable for centuries. You can walk into the Pantheon in Rome, built around 125 AD, and look up at an unreinforced concrete dome that has been open to rain and Roman weather for 1900 years. No steel rebar, no modern waterproofing. The oculus, the open hole at the top, lets rain fall directly onto the interior floor. The dome doesn't care. It's been doing this since Hadrian's time, and it's not planning to stop. But for most of modern history, engineers looked at structures like that and explained the durability with mass. Thick walls, the thinking went. The Romans built heavy, and heavy things last. Brute volume substituting for chemistry. That explanation is comfortable. It's also wrong. When researchers actually started comparing the chemistry of Roman concrete to modern Portland cement, what they found wasn't just a different recipe. It was a fundamentally different philosophy of what concrete is supposed to do. Modern concrete is engineered to be strong immediately. Roman concrete was, though the Romans didn't know the science, engineered to be strong eventually, and to keep getting stronger. These are opposite design logics, and the fact that one of them is no longer in use while the other is crumbling into the ocean is worth sitting with for a moment. The Romans called the critical ingredient pulvis putiolanus. We call it pozzolana. It's a fine reddish-grey volcanic ash that came primarily from the Bay of Pozzuoli on the southern Italian coast, at the base of a supervolcanic field called the Campi Flegrei, a name that translates aptly as the burning fields. The Romans didn't understand the chemistry, nobody would for another 18 centuries, but they observed through generations of practical building that when you mixed this specific ash with lime and water, something unusual happened. It hardened, even underwater, even in the rain, even in seawater direct from the harbour. That was an extraordinary property for engineers who needed to build harbour piers, underwater foundations, and breakwaters in the open sea. Before pozzolanic ash, large-scale underwater construction was barely possible. Mortar wouldn't cure below the waterline. With pozzolana, you could pour a harbour into the Mediterranean and come back in a season to find it solid enough to dock a warship against. Vitruvius, the Roman architect and engineer writing in the 1st century BC, described the ash with genuine fascination. He noted that, when mixed with lime and rubble stone, it produced a material that hardened in water and became, in his words, of one stone. He had no explanation for why. He recorded the observation, noted the source location, and moved on. What he was actually describing, though he had no way to know it, was a self-reinforcing crystalline reaction that would take 19 centuries of chemistry to fully understand.
And then the empire contracted.
The supply chains that moved pozzolana from Pozzuoli to construction sites across the Mediterranean began to fail. Not all at once, but gradually, as political and economic systems broke down across the 5th and 6th centuries. Medieval builders inherited Roman structures, but not Roman methods. They could see the quality of Roman concrete. They quarried it for raw material for over 1,000 years because it was easier than making new stone, but they couldn't replicate it. The formula didn't go into a vault, it dissolved into a logistics collapse. And for more than a millennium, it sat there, encoded in the surviving structures, waiting for someone with an electron microscope to read it back out. Modern Portland cement works through a reaction called calcium silicate hydrate formation. Mix the grey powder with water and it hardens through hydration. Calcium silicate compounds crystallize rapidly into a rigid paste. It achieves most of its compressive strength within 28 days. It's fast, it's predictable, and it dominates global construction because it can be manufactured consistently at industrial scale. The problem is what happens over decades. Portland cement is chemically stabilized by calcium hydroxide, unreacted lime that maintains a high pH environment inside the structure, which protects embedded steel from corrosion. But seawater, carbon dioxide, and moisture gradually consume that calcium hydroxide through a process called carbonation. As the pH drops, the protective environment disappears. Steel rebar expands as it corrodes. The surrounding concrete cracks. Water enters. The process accelerates. Modern structural concrete in marine environments isn't decaying despite its design. It's decaying partly because of its design. High strength, fast curing, steel reinforced, in an environment that systematically attacks each of those properties. Roman marine concrete has no steel, but that's almost beside the point.
The deeper difference is the pozzolanic reaction. When volcanic ash, rich in reactive aluminium and silica, meets calcium hydroxide from lime in a wet environment, they form something fundamentally different from what Portland cement produces. They form a calcium aluminium silicate hydrate gel. Over years, not days, that gel crystallizes into tobermarite, long interlocking mineral plates that grow through the internal structure like crystal fingers, filling micro cracks, reinforcing grain boundaries, welding the matrix together from the inside. And when seawater enters the mix, the aluminium-rich zeolite minerals in the volcanic aggregate react with the seawater to form phillipsite, another crystalline mineral that grows outward, plugging voids and gaps at the interface between concrete and ocean. The concrete repairs itself, not as a metaphor, chemically, continuously. As long as seawater keeps entering, the reaction keeps running. That is what modern concrete cannot do. Because Portland cement doesn't contain pozzolanic ash, and without the ash, there is no tobermarite reaction. There is no self-healing mechanism. There is just a pH that slowly drops and a material that slowly fails. So, what is the actual formula? This is both simpler and more specific than most people expect. The basic Roman marine mix, documented across multiple ancient sources and confirmed through analysis of surviving structures, is volcanic ash, lime, seawater, and aggregate. The aggregate was typically broken volcanic rock, ceramic fragments, brick rubble, or lightweight pumice, depending on what was available in the region. Romans weren't precious about it. The aggregate was structural bulk. The reaction happened in the binder. The ratios are what matter, and they're counterintuitive. The mix that keeps appearing in analysis of actual Roman structures is roughly 1 part lime to 2 or 3 parts volcanic ash by volume. Sometimes even less lime than that. The lime content is significantly lower than what modern builders instinctively reach for, because more lime sounds like more strength. It isn't. In a pozzolanic system, excess lime sits unreacted, waiting to be leached out by water. Less lime means more ash relative to binder, more surface area for the slow pozzolanic reaction, more tobermarite formation over time. The counterintuitive result is that the mix that looks weaker on day 1 is stronger at year 100. The lime itself came from a process called calcination, burning calcium carbonate, either limestone or seashells, at around 900 degrees Celsius. That's hot, but it's significantly lower than a modern Portland cement kiln. Roman lime kilns were simple and fuel-intensive, but they didn't need to be sophisticated. They needed to reach the calcination threshold and hold it long enough. Wood fires and stone-lined kilns did that. After burning, the quicklime was slaked, combined with water to produce calcium hydroxide, a thick white paste that generates intense heat during the reaction. This slaked lime was then blended with volcanic ash, aggregate, and water at the construction site, and for marine structures, the water was often seawater. Not because fresh water wasn't available, because seawater appears to accelerate the early stages of the pozzolanic reaction. The chlorides and sulfates in seawater seem to jumpstart tobermorite nucleation, setting the long-term strengthening process in motion faster than fresh water does. They didn't know why. They knew it worked. Here's where the replication attempts fall apart. And it happens with experienced builders, not just beginners. The lime has to be aged. Roman builders routinely matured their slaked lime for extended periods before use. Weeks at minimum, often months, in some documented cases, years. This aged lime, sometimes called fat lime or lime putty, has a fundamentally different microstructure from freshly slaked quicklime. As it ages in contact with water, the calcium hydroxide particles become progressively finer and more uniform. The surface area available for chemical reaction multiplies. The material becomes more reactive, not less, the opposite of what intuition suggests. When aged lime meets pozzolanic ash, the finer particle size drives a more thorough, more complete pozzolanic reaction. More tobermorite forms. The internal crystalline network is denser. The long-term strength is significantly higher. Freshly slaked lime mixed into volcanic ash and water will still harden. It will look like Roman concrete. It will even test reasonably well at 28 days. But the tobermorite formation will be slower, less complete, and the material won't develop the same long-term crystalline structure. You'll have built something that resembles Roman concrete the way a photocopy resembles an original. Close enough to fool a glance, not close enough to fool 2,000 years. This is the step that gets cut, every time. Because waiting 3 months to start pouring feels unreasonable when you have a project to finish. But the Romans weren't building for a project timeline. They were building for permanence. The lime aging wasn't a delay in the process. It was part of the process. You can accelerate a lot of things in this formula. You cannot accelerate the lime. Here is what this looks like under actual test conditions. A batch was prepared with lime putty aged 4 months, mixed with fine pumice powder. Pumice is a volcanic glass with reactive silica content comparable to true pozzolana, and coarse pumice aggregate for structure. Seawater used throughout. Ratio, 1 part lime to 2.5 parts pumice powder by volume, with aggregate added at roughly equal bulk volume to the combined binder. 2 blocks cast, 1 left to cure in open air, 1 submerged in seawater within 24 hours of casting. At 7 days, both blocks feel underdense compared to standard concrete. Rough, a little crumbly at the edges. The air-cured block is harder. The submerged block still has a slightly soft, almost chalky surface, which looks like failure. It feels like failure. Every instinct says the underwater block is behind. At 30 days, something changes. The air-cured block has stabilized but hasn't progressed much. The submerged block is noticeably denser. Tapping it with a knuckle produces a different pitch. Higher, more compact, less hollow. The surface that was soft has sealed itself into something smooth. At 90 days, the comparison is unambiguous. The air-cured block is strong and serviceable, but carries a small surface crack from drying shrinkage. The kind of microfracture that, in a marine environment, would become an entry point for saltwater attack. The submerged block has no cracks. Its edges are sharp. And across its surface, there's a faint pale mineral crust, tobermorite and philipsite, forming at the interface between the block and the water, exactly as they do in the ancient harbour walls. A steel nail drawn firmly across the air-cured block leaves a visible scratch. The same pressure on the submerged block produces almost nothing. The surface resists.
These aren't Roman harbour walls. 90 days isn't 2,000 years, but the mechanism is identical. And the most important result isn't the scratch test, it's the absence of cracking. The underwater block didn't just survive immersion, it used immersion. It looks like a material that wants to be in water. Now, what this formula actually is, practically speaking, it is not a fast material. If you need structural strength in a week, pozzolanic concrete isn't the answer for that application. Its strength curve is inverted relative to Portland cement. Modern concrete does the majority of its work in the first month and then plateaus. Pozzolanic concrete does a fraction of its early work, then compounds slowly, over years, over decades, potentially over a timescale that nobody in a modern construction schedule wants to think about. What it is, practically, a highly durable, chemically stable, self-reinforcing material for applications where permanence matters more than speed. Foundations that will sit in wet ground. Retaining walls in high moisture environments. Anything adjacent to tidal zones, groundwater, or coastal exposure. Garden structures meant to outlast the person who built them. Infrastructure you want your grandchildren to inherit rather than replace. The materials are accessible. Quicklime is available from building supply companies or producible from limestone or seashells with a sustained wood fire at the right temperature. Pumice in fine and coarse grades is sold through garden suppliers, pool supply companies, and natural building retailers. Aggregate from clean rubble. Seawater if you're near a coast, a salt solution otherwise, or fresh water if neither is available, accepting a slower start to the reaction. The cost is lower than Portland cement in most scenarios, especially if you're producing lime yourself. The time commitment is higher, mostly in the lime aging period before any mixing begins. The working properties are different. The mix is stickier and more forgiving of irregularity than bagged concrete, which is actually useful for complex forms and rubble fill. The service life, under the right conditions and the right application, doesn't have a confirmed failure point. The oldest surviving marine structures built with this method are still structurally sound after 2 millennia of continuous seawater exposure. Nobody knows when they'll fail. We don't have data for that because the data doesn't exist yet. There's a pattern worth noticing in how this formula disappeared. It didn't vanish because someone classified it. There was no suppression, no confiscation of the Vitruvius manuscripts. The Roman concrete formula didn't go underground. It evaporated upward through the collapse of the systems that made it practical. Pozzolana came from one bay on the southern Italian coast. When the trade networks that moved that ash across the Mediterranean stopped functioning, builders in Britain and Gaul and North Africa couldn't source the critical ingredient. The knowledge survived in text, the material supply didn't. That's the actual mechanism behind most lost techniques, not deliberate burial, supply chain fragmentation. The knowledge outlasts the infrastructure to apply it, and gradually, the knowledge starts to seem theoretical, historical curiosity rather than living method. It takes someone with an electron microscope and enough patience to drill a 2,000-year-old harbour wall to reconnect the observation to the explanation. Which raises a question about what we're currently pouring. Coastal cities are spending billions of dollars on Portland cement seawalls, pier replacements, and offshore foundations. Structures engineered with 50-year design lives, being built into an ocean that may look significantly different in 100 years. The formula that builds structures that improve with seawater exposure has been sitting in peer-reviewed literature since 2013. It's not proprietary, it's not expensive, it doesn't require industrial equipment. It requires a volcanic ash source, a lime kiln, and the patience to wait on the material to become what it needs to be. Self-reliance, in the deepest sense, isn't just about knowing how to start a fire or find water. It's about knowing which solutions have actually been proven, not by a laboratory under controlled conditions, not by a press release from a manufacturer, but by time. By structures that are still standing while the civilizations that built them are gone. There's another file in the vault that connects directly to this one, Roman hypercost systems, the passive underfloor heating method that kept buildings warm through alpine winters with no moving parts, no fuel on the burn cycle, just the slow physics of hot air and thermal mass. Same principle as this, different medium, different material, same design logic. Build it right once and it doesn't need you anymore. We'll open that one next.